Hey there. So up until this point, we've talked about the formation and the naming process that goes into binary compounds. Binary meaning that there's only two types of elements involved in making those compounds. But what if we have more than two? Well, that's what we're going to talk about today. We'll talk about compounds that have more than two elements involved. So let's go. Now, just as a bit of a reminder, we talked before about formula units. Formula units are the simplest whole number ratio of the elements involved in ionic compounds. And that's how we always report an ionic compound, with the lowest whole number ratio. So we have a few examples of formula units on the board. Here's one for magnesium chloride, here's one for aluminum oxide, and the ever classic sodium chloride. These formula units simply show us the ratio involved. So for this compound, we have one magnesium for every two chlorides. In this compound, we have two aluminums for every three oxides. And in this compound, it's 1-to-1, isn't it? One sodium for every one chloride. These binary compounds and others like them are composed of what we call monatomic ions. Monatomic ion, monoatomic, right? So it's just one atom involved. So the monatomic ions involved in magnesium chloride are one magnesium ion with a 2+ charge and two chloride ions with a -1 charge. Aluminum oxide is composed of two aluminum ions with a 3+ charge each, and then three oxide ions with a 2- charge each. NaCl is composed of one sodium ion with a +1 charge and one chloride ion with a -1 charge. Monatomic ions. Another term you need to know is that of the oxidation number. That's a term simply referring to the charge on a monatomic ion. So, the oxidation number of group 1 elements is +1. Remember, group 1 elements have one valence electron. They lose that electron to form ions of a +1 charge. That +1 is the oxidation number of those elements. Group 2 ions are +2, right? So, magnesium and calcium and strontium and barium all have an oxidation number of +2. The halogens have oxidation numbers of -1. So whatever the charge is on that monatomic ion, that refers to its oxidation number, or sometimes known as oxidation state. It is possible for a monatomic ion to have more than one oxidation number. In fact, many of the transition elements do just that. For example, iron can have more than one oxidation number. Sometimes we see iron in a +2 state, and other times we see it in a +3 state, depending on how many electrons have been removed from iron. Copper is another metal ion that sometimes has more than one state, having a +1 state or sometimes a +2 state. Not all transition elements have more than one state though. Zinc, for example, has only one state. It's a +2 state. But obviously you want to know, what do we do to tell them apart? Well, that's why we have a very special naming system that was developed for just this situation. It involves the use of Roman numerals. The Roman numeral that's used refers to the oxidation state of that metal. For example, if we have iron 3, in other words, iron with a Roman numeral 3, that means we're dealing with the iron ion that has a +3 charge. Iron 2, therefore, is the iron ion that has a +2 charge. Vanadium 5, yes, no kidding, vanadium 5. Vanadium 5 has a +5 charge, and platinum 2 has a +2 charge. You get the idea. We simply use the Roman number to designate which charge we're talking about, which metal ion we're using. But what if we have a formula involving a transition element? How do we know which ion we're talking about? Let's use two forms of iron oxide as an example. Generally speaking, we can count on oxygen having that -2 charge. Remember, oxide is in group 16, -2. So we can use that to determine which ion we're dealing with regard to the metal ion. Remember the balance, the teeter-totter? For this first example, FeO, if oxide is a -2 charge, and in order for that teeter-totter to remain balanced, iron must have what charge on it? Right, a +2. So therefore, FeO is iron 2 oxide, because iron has a +2 charge. What about Fe2O3? How do we determine what the oxidation number is of iron in that case? Let's use our teeter-totter once again. We know we have 3 oxides, right? With a -2 charge each. So we'll put those on our right side of our teeter-totter. And on the left side, we know that we have 2 iron ions. So if the right side of the teeter-totter is -6, that means the left side of the teeter-totter has to be +6. And so if we have 2 iron ions that represent +6, that means that each iron has to have a +3 charge. 2 times +3 gives us +6, coupled with the -6 on the other side levels out our balance. So in this case, we're dealing with iron 3 oxide, since each iron has a +3 charge. Now don't make the mistake of looking at the subscript on the iron and thinking that that's the charge. Because remember, we just figured out that this is iron 3 oxide. So if you looked at the subscript and said, oh, it must be iron 2, that'd be incorrect. We have to go through the process of figuring out what the ion is. But you can also do it in a slightly faster way. Let me show you. I like to call this the reverse swap and drop. Fe2O3. If we reverse swap and drop those numbers, we find that the 3 goes over the iron and the 2 goes over the oxide. Recalling that metals are generally positive and nonmetals are generally negative, that means we have iron with a +3 charge and the oxide with a -2 charge. Now, since -2 agrees with what we know about the oxide ion, that means that we can agree with the +3 for iron, iron 3 oxide. Like anything else though, folks, it just takes some practice to get it down. Many ionic compounds are composed of what we call polyatomic ions. So, if a monatomic ion is 1 atom, then polyatomic means, right, multiple atoms. Each of these polyatomic ions, though, are a unit. We treat them as 1 unit. And we have an entire table composed of polyatomic ions that will be most commonly used for us. Here's an example of one. SO4. We call this the sulfate group. Notice that there's a -2 charge on this sulfate group. That doesn't mean a -2 just on the oxygen alone, but rather this whole group is an ion with a -2 charge. That's a real important thing to remember. Whenever you see one of these polyatomic ions, you treat it as a unit, and we don't try to break it apart. It's like a team, and we don't break up a team, and the whole team has a -2 charge. So we can take these polyatomic ions and put them together just like we did with the monatomic ions. Let's take the sulfate group and pair it with sodium ions. Sodium has a +1 charge, and the sulfate group has a -2 charge. In the same way we did before, we'll swap and drop, and we get 2 sodiums and 1 sulfate group, Na2SO4, and we call it sodium sulfate. What? Oh, wardrobe change, yeah. All the big stars do it in their shows, yeah. What? No, it's no. It's not because there's some huge gap in recording from one day to the next. No, that's crazy. So, where were we? Oh yeah, polyatomic ions. You know, a lot of these polyatomic ions have oxygen involved. And so because of that, and because of the fact that most of them are negatively charged, we call them oxy-anions. Get it? Anion because they're negatively charged, and oxy because oxygen is involved in those polyatomic structures. Now, if you look at that table I discussed earlier, you'll notice that some of these names look extremely similar. Sulfate, sulfite, for example. What's the difference? As it turns out, 1 oxygen difference. The sulfate ion has more oxygens than sulfite. 1 more oxygen. I always like to think of it this way. The A is fatter than the I, which means more oxygen has been consumed. How about that? We also see this in phosphate, phosphite, nitrate, nitrite. So anytime you have 2 oxy-anions that look very similar, like SO4 and SO3, you'll know which one has the ATE ending because it will have more oxygens involved. We could even take this one step further with the use of the prefix per and the prefix hypo. For example, chlorate is the ClO3 ion. It has a -1 charge. Chlorite is ClO2, and it also has a -1 charge. Notice that the chlorate has one more oxygen than the chlorite does. We can go a step above and a step below. In other words, perchlorate is when we have ClO4 with a negative charge. One extra oxygen above chlorate. And on the other end of the spectrum, we can have a chlorine oxyanion with one less oxygen than chlorite does. ClO with a negative charge. We call this hypochlorite. We sort of think of hypo as less than normal, right? So maybe that'll help you think of hypochlorite as being less than chlorite. This naming system can be used with other elements involved as well, such as bromine or iodine, even sulfur. You can have the persulfate ion, which is a SO5 with a -2 charge. You can have hyposulfite ion, which is SO2 with a -2 charge. If you're wondering about a way in which you can remember which ones have ATE endings and ITE endings, here's something I think will help. Let's look at the nonmetals. These four that are highlighted, I like to call my 4 for 4. And here's what that means. If any of those four have 4 oxygens attached to them, they'll have the ATE ending. PO4, phosphate, SO4, sulfate, ASO4, arsenate, SeO4, selenate. Apart from that, any of the others that are highlighted will only need 3 oxygens to have the ATE ending. BO3, borate, CO3, carbonate, NO3, nitrate, FO3, fluorate, ClO3, chlorate, BrO3, bromate, and IO3, iodate. Hopefully that helps you remember which ones require 4 and which ones require 3. Remember, if you have less oxygens than what you want for the ATE ending, that gives you an ITE ending. The ATE ending gives us more oxygen than the ITE ending does. If we add the prefix PER on the front, that's even more than ATE. And if we use the prefix hypo, that gives us less than ITE. Now I want to draw your attention to one thing about this naming system. Remember that if we have an IDE ending, we're talking about a monatomic ion. Okay? Just want to bring that back to you for a moment. Monatomic ions have an IDE ending. So if it's something other than oxygen, we're saying that no oxygen is attached to that ion. If we see an ATE ending or an ITE ending, we know that those are polyatomic. What about charges? Is there a way of recalling what the charges are on these? Actually, that's not too difficult either. For instance, if we look at these oxyanions that contain halogens, all of them have a -1 charge. That's pretty cool. So if you recognize you have chlorine or bromine or iodine in one of these oxyanions, you can know it probably has a -1 charge. The oxyanions from group 16 tend to have -2 charges. Sulfate, sulfite, selenate, selenite. And with the exception of nitrogen, the group 15 oxyanions have -3 charges. Phosphate, phosphite, arsenate, arsenite, all have -3 charges. The others you'll probably become accustomed to and remember a little better as you use them more frequently. For example, the nitrate group. We use that quite frequently. It has a -1 charge. Carbonate's another one that we use quite frequently. It has a -2 charge. Okay, here's your homework, and it's a two-parter. First of all, see if you can name these 2 compounds. You can simply type their names in the LMS. That's part A. Here's part B. I want you to see if you could write the formulas for these 2 compounds. The first is calcium phosphate. Calcium phosphate. The second one is iron 3 chlorite. Iron 3 chlorite. And remember, if it requires more than one of the same oxyanion, you need to use parentheses. Okay? You can put your answers on the LMS. That's all the time we have for today. Today we talked about polyatomic ions. Ones like the oxyanion, things like sulfate and sulfite, phosphate, phosphite, and so forth. And then we discussed the naming conventions we use in dealing with the ones that have the ATE ending and the ITE ending, when we use the PER prefix or the hypo prefix, and we even talked about the charges on some of these oxyanions as well. I hope this has been beneficial to you, and if I can help you in any way, please let me know. Until the next time, God bless.